Hey everyone, today we're going to be going through Worksheet 5.3 Exercise 8. And if we look over the question, Part A introduces the function g of x, defined as the integral of f of t from t equals -4 to t equals x. And we need to find g -1, g prime -1, and g double prime -1. So if we were to write that down, g of x equals -4x f t dt, and we need to find g -1, g prime -1, and g double prime -1. So for g -1, this is a definite integral from -4 to -1 since x is defined as -1. So we can just simply plug it in as -4, -1, f of t dt. And this is the net area under the graph of f from -4 to -1. And looking at the graph, you can see that this region forms a trapezoid, like so. And just simply finding the area of this trapezoid would give us the integral of -4 to -1 f of t. So we know the area for trapezoid is 1/2 base 1 plus base 2 times height. And looking at the graph, we know that base 1 is 1, 2, 3 units, and this is 1, 2, 2 units. So we can see that 1/2 3 plus 2 times height would be 1, 2, 3 as well. So we would find that the area of this trapezoid is 15/2. Therefore, g -1 equals -15/2, since the region is below the x-axis, so the area will be negative. Now going over g prime -1, using the first part of the fundamental theorem of calculus, the derivative of a function defined as an integral is just the integrated evaluated at the upper limit, which means that g prime x would just equal d dx integral -4x f of t dt. And to put it in simple terms, that just means that that is fx. So to find g prime -1, that would just mean that g prime -1 equals f -1. And since we're provided with the graph of f, we can see that at x equals -1, g prime -1 equals -2, since we just look at the y value. Therefore, it's simple that g prime -1 equals -2. And to find g double prime -1, this is the g prime x is the derivative of g prime x, which is f prime x. So g double prime x would equal f prime x, and which means g double prime -1 equals f prime -1. This f prime -1 represents the slope of the graph of f at x equals -1. So if we look at the graph at -1 at this point, the slope of the graph of f is not the same immediately to the left to the right of x equals -1. So it has a sharp turn a corner, you could say, at x equals -1, which means the function isn't differentiable at x equals -1. So therefore, g double prime -1, g double prime -1 is d and e. Moving on to part B. Part B asks for the x-coordinates of the points of inflection for g of x on the open interval -4 to -3. One concept to keep in mind is that a point of inflection occurs where the second derivative changes sign. So to find where g has a point of inflection, we have to find where g double prime of x changes signs. And we know from the previous question, part A, that g double prime x is equal to f prime x. So gx has a point of inflection where f prime x changes sign. And f prime x is the slope of f. And f prime x changes sign when the slope of f changes from positive to negative or negative to positive. Another way to think about this is that the points of inflection of g occur where g prime x changes from increasing to decreasing, or vice versa, since g prime x equals fx. So we're looking for where the graph of f changes from increasing to decreasing or decreasing to increasing. So if we look at the graph, we can see that f is increasing from negative x to 1. I'll make the increasing parts blue. And we can see that it is decreasing from 1 to 3. Since this has a positive slope, and a negative slope. So we can conclude that the function of f changes from increasing to decreasing at the point x equals 1, which is the same as the local maximum for f. Therefore, g of x has a point of inflection at x equals 1. Moving on to part C. Part C introduces the function hx, defined as integral x to 3 ft dt. We need to find all values of x in the closed interval -4, 3, for which hx equals 0. Hx equals 0 means that the net area under f from x to 3 must be 0. This can be written as an expression as hx as integral x to 3 ft dt equals 0. Just by looking at the question, we can see an obvious solution. If the upper and lower limits of integration are the same, the integral is 0. Which means when x equals 3, the area must be 0. Which makes x equals 3 one obvious solution. To find the other solutions, we need to check other points where the net area from x to 3 is 0. And we can do this by analyzing the graph of f. And we see that from 2 to 3, the function f forms a triangle under the x-axis, which means it's going to be a negative value. And we see that the base is 1 and the height is 2. And the triangle area is base times height times 1/2, which means the area of this triangle will be -1. And we see that there's another triangle on the interval 1 to 2 with the same exact dimensions, which means the area for this triangle will be +1. And this can be rephrased using integrals by saying, since the integral from 1 to 2 is 1, and the integral from 2 to 3 is -1, their sum is 0. And this can be written as an integral expression. Integral 1 to 3 ft dt equals integral 1 to 2 ft dt plus integral 2 to 3 ft dt, which equals 1 plus -1 equals 0. That makes our second solution to this problem x equals 1. To continue, we can continue backwards from x equals 1. And we see that there's another triangle forming from 0 to 1. And this also has the same dimensions as the other two triangles, meaning the area will be +1. And we see another triangle forming under the x-axis with the same dimensions. And since it's under the x-axis, it will be also -1, meaning the integral from -1 to 0 and 0 to 1 is also 0. And if we combine all of these, we also get 0. And this can also be written as an integral expression using -1 integral -1 to 3 ft dt equals integral -1 to 0 ft dt plus integral 0 to 1 ft dt plus 1 to 2 ft dt plus integral 2 to 3 ft dt. And this would equal -1 plus 1 plus 1 -1, which gives us 0. Meaning the third solution to this problem is x equals -1. Meaning the values for which hx equals 0 are x equals 1, x equals 3, and x equals -1, which would be the final answer for part C. Moving on to part D. Part D asks for all intervals on which h is decreasing. A function is decreasing when its first derivative is negative. This can be written as h prime x is less than 0. And we can find h prime x using the fundamental theorem of calculus. Since hx equals integral x to 3 ft dt, we can rewrite this as negative integral 3 to x ft dt. Therefore, h prime x equals negative d over dx integral x 3 ft dt, which equals negative fx. And since we know that h prime of x has to be less than 0, we can say that negative f prime x, negative f x is less than 0, which should be the same as writing f of x is greater than 0. By this, we can say that hx is decreasing when the graph of f is above the x-axis. What that means is that on the graph of f, for the parts that the graph is above the x-axis, is the part that hx is decreasing. And looking at the graph of f, the function is positive on the open interval 0 to 2. That will be all of this part. Therefore, h is decreasing on the interval 0 to 2. So we can conclude that h is decreasing on the interval 0 to 2. Thank you.